Good day, everyone. Let me start with a simple question. Have you ever played with magnets and noticed how they either snap together or push apart, even without touching? That invisible push and pull comes from something we call a magnetic field. Now, here's where it gets fascinating. This invisible field is not magic at all. It actually comes from the tiniest building blocks of matter. Deep inside atoms, electric charges are moving, and electrons possess a special property called spin. Together, these motions make each atom act like a tiny bar magnet, or in physics terms, a tiny magnetic dipole. When millions upon millions of these atomic dipoles align in the same direction, we get a magnetic material strong enough to attract nails, stick to your fridge, or guide a compass needle. But how do we visualize something we can't see? That's where magnetic field lines come in. These are imaginary loops that help us represent the field. They always emerge from the north pole of a magnet and curve around to enter at the south pole, and here's the key: they never stop, they always form closed loops. As you can see when you place a bar magnet under iron filings, those beautiful curved patterns you observe aren't random. They are actually the magnetic field lines revealing themselves to you. A simple classroom activity, yet it shows the invisible structure of the field in a way that's truly mesmerizing. So to sum up, magnetism isn't just a curious property. It's the collective behavior of countless atomic dipoles working together. And magnetic field lines are our way of mapping this invisible force from the tiny scale of atoms to the grand scale of Earth itself. I hope this gives you a clearer picture of what lies behind those everyday magnetic tricks. In our next session, we'll dive deeper into how these fields interact with matter and power some of our most important technologies. Have you ever wondered, if magnets have a north pole and a south pole, could we isolate just one of them? Could there be a magnet with only a north pole or only a south pole floating around in nature? It's an exciting thought, but here's the truth: no one has ever found such a thing. Unlike electric charges, which can exist separately as positive or negative, magnetic poles never exist alone. We call this the non-existence of magnetic monopoles. Every magnetic dipole, whether it's a tiny atomic dipole or a bar magnet you hold in your hand, always comes with both poles. They are inseparable companions. If you try to cut a bar magnet in half, you don't isolate the north from the south. Instead, you simply end up with two smaller magnets, each with its own north pole and south pole. And if you cut them again, the same thing happens. As you can see in the diagram, the field lines never start or end on a single pole. They always form closed loops, flowing out of the north, curving around, and returning to the south. That's why an isolated magnetic pole has never been observed. This idea is not just a curiosity, it connects deeply with Gauss's law for magnetism, which tells us mathematically that the net magnetic flux through any closed surface is always zero. In simpler words, there are no magnetic charges acting as single sources or sinks of magnetic field lines. So, to sum up, magnets always exist as dipoles with both poles intact. Magnetic monopoles remain one of those fascinating what-if questions in physics, a mystery that continues to inspire scientists, but so far, nature seems to firmly forbid them. I hope you now see why magnets can never be split into isolated poles and how this connects to the very laws of magnetism. In the next lesson, we'll explore more about how these fundamental properties shape the magnetic world around us. Now let's introduce the star of our concept, Gauss' law in magnetism. This law tells us that the net magnetic flux through any closed surface is always zero. Let me say that again. The total magnetic field passing into a closed surface is exactly equal to the total field passing out. The formula for this is Integral over a closed surface of vector b dot vector dA equals 0. Why? Because magnetic field lines never begin or end at any point, they always loop back, forming continuous paths. This makes magnetism fundamentally different from electrostatics, where field lines start or end at electric charges. Think about this. If a magnetic field enters a closed surface, where does it go? Does it simply disappear inside? The answer is no. Because of Gauss's law in magnetism, whatever field enters must also exit. That's the heart of the idea of zero net flux. Since the total magnetic flux through a closed surface is always zero, magnetic field lines must maintain continuity. In other words, they cannot begin or end at a single point, but must form closed loops. That's why, unlike electric field lines that start on positive charges and end on negative charges, magnetic field lines just keep looping endlessly. This law also tells us something powerful. Magnetic field lines can never converge into or diverge out of a single point because magnetic monopoles simply don't exist. Every field line that enters has to leave somewhere else, keeping the balance perfect. From a practical perspective, this property makes life much easier for physicists and engineers. It allows us to analyze symmetrical magnetic field configurations with much greater clarity. Take the case of a toroidal solenoid. Inside, the magnetic field lines are tightly wound and form closed loops that never escape, a direct, real-world confirmation of zero net flux in action. So to wrap it up, zero net flux is not just a mathematical statement, it's nature's guarantee that magnetic field lines are continuous, unbreakable loops. This insight is one of the key reasons why Gauss's law in magnetism stands apart from its electrostatic counterpart. I hope this helps you see how such a simple rule, that what goes in must come out, actually reveals a deep truth about the magnetic universe around us. In our next session, we'll look at how this principle supports advanced applications of electromagnetism. Let's start with a simple thought. If magnetic field lines are continuous and never begin or end, how do we express that idea mathematically? This is where the flux equation comes in. The law states that the total number of magnetic field lines entering and leaving a closed surface is always equal. In other words, no field line is ever lost or created inside, it simply passes through. Mathematically, we express this using the surface integral of the magnetic field B over a closed surface. The equation reads, phi sub B equals the closed surface integral of B dot da equals 0. Here, phi sub B is the net magnetic flux through the surface, B is the magnetic field, and da is the infinitesimal area vector. Now, what does this really mean? The integral result being 0 tells us that magnetic fields have no source or sink. Unlike electric fields, which can begin on a positive charge and end on a negative charge, magnetic fields must always loop back. They cannot start, they cannot stop, they are continuous by nature. As you can see in the diagram of a uniform field passing through a closed box, the field lines that enter are exactly balanced by the lines that exit. The net flux adds up to 0. This beautifully validates the idea that magnetic field lines must always form closed loops. It's a powerful statement about the very nature of magnetism and one of the key features that makes it fundamentally different from electrostatics. So, to wrap it up, the flux equation is more than just math, it's a confirmation of nature's rule that magnetic fields are continuous and self-sustaining. I hope this helps you appreciate the elegance of Gauss's law for magnetism. In the next session, we'll see how this principle connects with other Maxwell's equations to form the foundation of electromagnetism. Let's work through a classic example to see Gauss's law in magnetism in action. Imagine you place a bar magnet inside a cube. The question is, what is the net magnetic flux through the cube? At first glance, you might think, well, magnetic field lines pass through the cube's faces, so surely some flux must remain. But let's break this down step by step. Step 1. Treat the bar magnet as a magnetic dipole, with continuous closed-loop field lines emerging from the north pole and entering into the south pole. Step 2. Apply Gauss's law for magnetism. The net flux phi sub b is equal to the closed surface integral of b dot da, and that equals 0. Step 3. Even though field lines clearly pass through the cube's surfaces, the key is that the outward flux is exactly balanced by the inward flux. For every line leaving, another line enters, so the totals cancel out. Therefore, the answer is phi sub b equals 0 Weber. And the reason? The absence of magnetic monopoles. Without isolated poles, the flux across a closed surface always sums to 0. As you can see in the diagram, the field lines form loops that cut across the cube, but no net flux escapes. This simple example beautifully demonstrates how Gauss's law for magnetism works and why it's consistent with the closed nature of magnetic field lines. So the takeaway, no matter how you enclose a magnet in a cube, a sphere, or any closed surface, the net magnetic flux will always be 0. Before we wrap up, let's quickly bring together the key takeaways about magnetism and Gauss's law. First, remember that magnetic field lines are special. They never begin or end at a single point. Instead, they always form closed loops. This simple fact is central to understanding magnetism in matter. Now, Gauss's law in magnetism states that the net magnetic flux through any closed surface is 0. What goes in must come out, and that's only possible because there are no isolated magnetic charges. This makes magnetism fundamentally different from electrostatics, where electric field lines can start at positive charges and end at negative ones. This directly reflects the non-existence of magnetic monopoles. Every magnet has both poles, and cutting one only produces smaller dipoles, never an isolated north or south pole. Finally, this law gives us a lot of symmetry in analyzing magnetic fields. Whether it's in solenoids, toroids, or more advanced applications, the idea that field lines must loop back ensures consistency in how we understand magnetic fields in real systems. So, to sum up, Gauss's law tells us that magnetic flux across a closed surface is always 0, confirming the looped nature of field lines, the absence of monopoles, and the symmetry of magnetic field behavior. I hope this recap helps you connect all the dots. In our next session, we'll take these ideas further and see how they integrate with the grand framework of Maxwell's equations.